In our universe, all things are driven by energy. Energy powers our sun, our environment, our society, even our bodies. Energy is life. New and profound advances in science and engineering are allowing us to harness this energy abundance in marvelous new ways. To create clean, affordable, and reliable energy for all Californians. The SoCalGas Research Development and Demonstration Program has enlisted an incredible team of experts in science, engineering, industrial technology, and environmental policy to identify, build, and implement these transformational technologies throughout society. Collaborating with the world's top institutions, we have deployed over $73 million on hundreds of groundbreaking projects over the past 5 years. Hyatt Hydrogen, which could enable transporting hydrogen through existing infrastructure to power fuel cell vehicles and facilities. Doosan Mobility Innovations hydrogen drones that have 4 times the flight capacity of lithium-ion powered alternatives. And hydrogen-powered yard trucks that can move massive shipping loads for 20 hours per day with 0 emissions. These revolutionary projects are saving energy, reducing emissions, and improving air quality, as well as increasing energy safety, reliability, and affordability for all. At SoCalGas RD&D, we believe in clean energy abundance. So we are sharing this pivotal research in order to deploy these innovative technologies across the world. Because energy is life. And we believe a clean energy future will bring a better future to everyone.
Good morning, everyone, or afternoon if you're on the East Coast. Thank you for joining us today. Let's see. I think I forgot, sorry. Oh, there we go. Just wanted to welcome you all to our webinar to present the Explorer Crack Sensor and the robot program that we funded through NYSEARCH. And first, before we get into the research, want to take you through just some logistical things. The GoToWebinar, oh, did it go up? Oh my God. Sorry. Okay, GoToWebinar, it's scrolling, Heather. I don't know how to make it stop scroll. Okay, well, I'm just going to keep talking and the presentation is going to keep going through. So there's a little question bar to the right-hand side on your screen, and that's where you can type any questions that come up during the meeting, or you can also at the end of the meeting, we'll have presentation, we'll have time for you to raise your hand and you can go off mute and ask your questions as well. And just wanted to give you just a quick overview of the RD&D program that SoCalGas funds. We have several different research groups, programs, and this is presenting under the gas operations RD&D program. My name, I forgot to introduce myself. I'm Karen McInnes, and I am the team lead of the gas operations RD&D program. And we fund a lot of work, a lot of research. Just give you a quick highlight. This is the number of projects that we funded in 2022. If you want to know more about what we've done as a program across all of the different areas, you can go to our RD&D annual report for 2022. It gives an overview of everything that we fund, support, as well as summaries of every project that was active in the year. And we also have ways to keep connected. We have a website and we have an email address where you can send us questions, information, research that you think that we should be aware of. But that's enough of the intro and administrative piece. I'd like to get started by introducing Travis Serra. Travis is the Director of Integrity Management, and he has been actively part of this program and getting it to where it is today. So Travis, take it away.
Okay, thank you, Karen. Good morning or good afternoon, everybody, wherever you're calling from. I'm very excited to be here. When we were going through the preparation sessions for this webinar, I was asked if I would like to give the introduction. I leapt at the opportunity because I really want to communicate that I have been involved in this type of research for quite some time now, decades. And NYSEARCH and Daphne and her team have been, in my view, ideal partners. I mean, just imagine, and this is a true story, imagine you wake up one day and you say to yourself at work, boy, I wish I had a, fill in the blank. I can't speak highly enough about Daphne and her team. They are the ones who fill in that blank. And the proof is in the pudding. You don't even need to believe me. You can just simply see the suite of results that her organization has produced under her leadership, and it speaks for itself. Decades ago, there were no such thing as robotic inspection tools. We use them routinely now to solve some of the most difficult problems in our industry. And I know for sure today, we are asking ourselves, okay, what's the next step forward? What does the future look like? And Daphne and her team are actively working on making that a reality. They're a top-notch organization. I think they're a symbol for how R&D should be done, a wonderful example of how partnerships should work between operations and R&D and the engineering consultants who make these things happen. So without further ado, I know we want to get right to the material. I'll hand it off to Daphne with my enthusiastic endorsement and my thanks to her and her team for all the great work they've done over the years. Daphne, it's always a pleasure to see you, and I'm really looking forward to this webinar. So thank you very much.
Well, thank you, Travis. Karen. I'm blown away from that introduction. Never had such an introduction. It's really not me. It's the great team behind NYSEARCH, the members, Dr. George Veratis, and now Suzy Chaillou. You're going to hear a lot from today, and basically, a lot of work by a lot of people to get here, including Travis Serra and SoCalGas. With that, I'm here to just sort of give you an overview of NYSEARCH and what led to the crack sensing program, because R&D like this takes a lot of foresight, takes a lot of planning, and other successes. So on my first slide, there is a picture of an original crack module on a robot in one of Pipetel/Invadane, now Intero's packaging tray at a test bed that one of our members has leased to us in upstate New York. So that was long ago, but it was one of the steps along the way. And there's lots of different illustrations of steps along the way in this presentation today, but I wanted to give you a sense of, we're going to talk today about the evolution of R&D that was spearheaded and championed by SoCalGas and other members of NYSEARCH, but particularly SoCalGas in this case, that led to a success that now is, available and being offered commercially by Intero and Pipetel. So with that, just brief things on NYSEARCH for those who are not familiar. We represent the local distribution companies in the gas industry, 20+ members. It's an entirely voluntary program. People join as a member for a relatively small cost and can then decide on projects one by one. And so we're going to talk about a package of projects today. The key for the gas industry in this research model was that they do have to do things on their own, but they also work together to not be redundant, to collaborate, and to maximize the value of the R&D dollar. And that's what happens in this NYSEARCH model. And we also try to stay informed on state-of-the-art technologies and make sure that our members are exchanging. And we have such a good collaboration with a long-term history like Travis described. So not very sophisticated, a footprint for us where we have members. NYSEARCH implies New York. We just had name recognition, so we've never changed that. To give an idea of our portfolio, we do focus on gas operations. We have some utilization, but primarily gas operations. And the leverage ratios for large, medium, and small companies is shown there. Pipeline integrity, this area that we're talking about today, has been a large part of our program in gas ops and safety since the early 2000s and before. Coming on strong these days for everyone is low carbon fuels. There are expenses that go along with building robots that tend to overshadow other projects, but we have important projects in leak detection, reducing greenhouse gas emissions, pipe location, etc. Just some links, it's in the handout if you wanted to see what's available on the public section of our website. We are a small organization with a handful of staff, but we try to keep non-members and the public informed. We have a good staff here with a lot of interesting projects we put in technology briefs and in various newsletters and papers. So getting to the interesting aspect of today's session, we wanted to start with just a quick explanation before we got to crack sensing, which is, I imagine, why most folks are here today. In the early 2000s, we had visions with folks in the East and the West about being able to inspect what we called at the time unpiggable pipes. And that led to Explorer. The name Explorer came in the probably 2010 or 2008 timeframe. But we originally had a vision back in 2000 for inspecting these, quote, unpiggable pipes that were 6 inches diameters up to 36. And the thing is, LDCs, not necessarily all transmission companies, but LDCs who own transmission pipes have operational features that are challenging. Back-to-back bends, elbows, verticals, tees, all kinds of things. So that's what we went after. The fill in the blank, Travis, you're very flattering. We tried to fill in the blank in a number of ways here, but it took a long time to fill in all these blanks, and we had some very talented organizations along the way. So fast forward to 2010, 2011, we commercialized with Invadane, now Intero, through a license. They have commercialized initial sizes in 2010 and 11, and by 2017, roughly all the sizes of the Explorer platform of inspection robots. So you see an example there from their website, the Pipetel website, and some example data. So real quick, I have 4 frames here in a very busy chart, but for R&D wonks, every bubble here represents a major aspect of starting in 2001 and getting to 23. Generally, the stuff to the left of the blue bubble in the middle are early stage technology providers, co-funders like Department of Energy, various work that we had to do with funders to break down the sizes into different platforms, and Travis and those at SoCal on the early days remember that. And then searching for prospective commercializers. Been actually across the world with one of my colleagues looking for commercializers, and we found Invadane as also one of our sensor providers. And on the right, we just get the crack sensing program that we're going to talk about today, and all the different things that had to be set up for this license in this business. One last thing from me. Oh no, 2 last things from me. So the magnitude, we were asked to give you the magnitude. It didn't come easy. There was a lot of investment by the industry, a lot of time by folks on R&D as well as government R&D programs, providers, 27 completed projects to get where we are today. There's 1 interactive, 2 that are pending. Just on crack sensing alone, it's been a $5 million investment by the NYSEARCH group, and then there's been other investments by the others. And if you look at the total robotics program outside of that, not including government contracts, it's roughly 40 million. And the government contracts roughly 10 million. And thank you to Pipetel, because there's jobs out there that occasionally we get to see these exciting pictures of what has come to pass for Intero and Pipetel. And the key of this program is to get improved safety and technology that's using and providing benefits to the industry. So with that, I just want to say one last thing to lead to Suzy's talk about crack sensing. And it was SoCalGas in 2010 that made the call to us after Explorer was ready to go and said, hey, we really need to get on crack sensing. We had corrosion sensing. Travis, I credit you for the idea of going after transverse MFL. And so we know others were also working on crack sensing, but maybe for other applications. And today, revisiting today where we are, we ended up with a weld crack sensor. It fits nicely with some of the top priorities for assessing cracks or crack-like features. and verifying information that SoCal wants to have verified. And I imagine that applies to others that are on the phone today. Furthermore, as we go into emerging fuels, would this not be an opportunity for even more assessment? Should blended hydrogen be a part of the mix going forward? With that, I am going to welcome Suzy, my colleague, Senior Project Manager from NYSEARCH.
Great, thank you, Daphne. Great, so thanks, Daphne. So like Daphne said, I'm going to be going through the evolution of our crack sensor technology. It has been a long and an adventurous road, to say the least. So some kind of building off of what Daphne has discussed earlier about the Explorer program, we wanted to maintain that performance and add the crack sensor technology to the robot. So being able to complete one pass and collect data with the current technology like MFL metal loss and the additional weld sensor technology would be ideal, as it would cut down on the inspection time and cost doing one pass versus two, one for each of those technologies. Additionally, the design targeted the 2026 Explorer series for the 20 to 26 inch pipes, where the wall thickness is typically ½ an inch, which is thicker. The wall is more of a challenge when the wall is thicker to detect the cracks, especially root cracks. And we wanted to be able to traverse the same unpiggable pipelines that Daphne did discuss. So there's been a lot of work and technology development to get where we are today to detect cracks in the pipeline. Some of the early crack sensing designs were detecting cracks on the full circumference of the pipe. One of the products used transverse magnetic flux leakage, TMFL, and electromagnetic acoustic transducer technology, EMAT. The second design is a full circumference anthroposophic magneto resistance, AMR eddy current sensor, which we'll get into both of these technologies a little bit later in the presentation. I kind of just wanted to give an overview of some of the early designs that we looked into. When we first started this concept, we worked with the NYSEARCH members to understand the R&D priorities for the crack detection and where they're located on that pipe. So this table is showing those priorities of the types of cracks typically seen in the industry. The first priority is seam weld cracks along with large flaws, pipes within casing, corrosion, internal, external cracks, which I show on the pipe here in this nice little graphic. So priority 1 is depicted with the one bubble with the casing and the seam welds. And then the second priority was cracks on the girth weld and tight cracks. You can see here's a girth weld and here as well. And then the third priority was cracks on the base material, and that's depicted here as well, having cracks on the base material. But seam weld cracks have always been the #1 priority from the beginning of this journey. So NYSEARCH's journey into crack sensing began in 2011. We started with the full circumference TMFL and EMAT sensor. Although very successful, there were some challenges with that design, so we continued to investigate technologies to optimize that design. So in 2013, that's when we moved to that AMR eddy current design, which did also have some challenges as well, but I'll get into these designs and challenges into this presentation. But in 2016, we looked at the priorities again and decided to focus on seam weld crack, since that was our first priority, like I just discussed. And that is what we have commercialized today. So at the bottom of the graph here, in these gray boxes, I listed the funders for each of these technologies. And as you can see, I bolded SoCalGas because they did fund all these technologies and did enjoy us on our journey here. So the first technology I'm going to talk about today is the TMFL EMAT sensor. Current technology on the Explorer Robot can determine the metal loss on the pipe due to corrosion, which is the magnetic flux leakage MFL sensor. These sensors magnetize the pipe wall in the axial direction, thus providing great capabilities for corrosion defect detection. But when we rotate 90 degrees, the magnetization detection of axially aligned cracks can be achieved. And this is known as transverse magnetic flux leakage, TMFL. And the other part of this sensor's technology is the EMAT. This brings the ultrasonic methods to applications where we don't need gel or water to bring that acoustics out. The EMAT sensor system requires a magnetic field in the base material along with a pulse coil that causes an acoustic pulse to travel through the material. These two technologies, when working together on the robot, were successful in finding the cracks on that full crack sensor pipe. So this technology was successful. It was able to detect cracks at depths that were greater than 25% of the wall's thickness. Since it was a full circumference crack sensor, it was able to detect those cracks along the full surface of the pipe in one single pass. But it was separate from the MFL mechanical damage sensor. So 2 passes would be required for a standard MFL mechanical damage and then another one for this crack inspection. However, the commercializer did believe it was too heavy and difficult for the Explorer robot to maneuver, and it was sensitive to debris and girth welds. So we did end up looking at other technology, like I said. But to kind of bring in that first chart that you'll be seeing a few times throughout this presentation to kind of show each technology and where it stands on our priority list for these R&D priorities, the sensor worked great and it met all the specifications that it was designed to do. But since our commercializer did believe it was too heavy to maneuver, we did seek other technologies, but it did meet all of our #1 priorities. It met all of them except for being able to detect on girth weld cracks. So then the second technology that we want to talk about today is the anisotropic magnetic resistive AMR eddy current design. Eddy currents have a fundamental depth limit defined and measured by the skin depth. This is the depth at which electromagnetic currents protrude into the surface of the material, and it depends on the material's conductivity and permeability. Some flaws were established to be deep enough so that were estimated to be deep enough so that only a tiny fraction of the eddy currents will reach them, making it unlikely that they could be seen with this eddy current sensor. When a conductor is placed in a changing magnetic field, the induced current on the conductor is termed as an eddy current. Eddy currents are named because they look like whirlpools or eddies, kind of like we're showing here. So this was also a great design. It was lightweight and easy to maneuver. It was a full circumference crack detection design, so it could detect cracks on the base material and on the seam welds. However, this was sensitive to debris, and it wasn't great for the larger pipes due to the thicker walls in the larger pipes. And then the downside of that eddy current is the depth of penetration through those pipe walls. So this technology was really only good for pipes that were about 14 inches or smaller in diameter, since they have the smaller wall thickness. And additionally, because the eddy current was a full circumference crack sensor, this also needed 2 passes, one for the standard MFL for mechanical damage and this technology for crack inspection. And so this technology satisfied most of all of our R&D priorities that we talked about earlier. However, this sensor was sensitive to debris, but it did work well for pipes that were 14 inches or less in diameter. So getting into our current design for our Seam Weld sensor, in 2016, when we looked at the R&D priority list again, we decided to target the seam welds and develop a Seam Weld Crack Sensor. And making that decision to do Seam Weld Crack Sensor, we decided that it would be great if we could do 1 pass, if we could build a robot with the MFL tool for mechanical damage and the Seam Weld Crack Sensor. So we would only have to do one pass instead of two, like our previous two designs were for. So to satisfy those requirements, we designed a crack sensor module that would have two sensor modules, one in front of the MFL tool and one behind the MFL tool. This design would have the full coverage of the seam weld and have the MFL metal loss module as well in the center. The way this design would work is the two modules would work in concert. The front would act as the leader and the second would act as a follower. The first one would find the girth weld and then look for the seam weld. Because it does miss the beginning of the seam weld, but once the leader locates the seam weld, the second one would move to the seam weld before it reaches the girth weld. So I have a video. This is detecting the leader. This is the follower, same here. And this diagram shows it, but I do have a video if I can. I don't know how to. I think I might have to get out of, oh, here we go. So the video shows the leader. It finds the girth weld and it's now looking for the seam weld to move into position. It now communicates to the follower where the seam weld is so it can transition before it gets to the girth weld. And with both of these working in concert, you can get a full 100% coverage of the seam weld. And I'll play it one more time just to get a feel for what the two working together looks like. Things that are going on in this robot, we're looking for the girth weld to signal the seam weld location change, and we're looking to read the welds on the cracks. So the early phases of this project, we struggled with finding the low signature welds, the ERW welds. So we went back to the older versions of the crack sensing that we've been talking about today and reevaluated those technologies to determine the best for weld detection, especially for those low signature welds. We looked at that AMR eddy current and the EMAT technology for seam weld detection, but they both displayed limitations and would add complexity to the system. The CMFL did capture a clear signal for 3 different seam weld profiles, the low, medium, and high, and had clear scan results. The CMFL system is the same technique we used with the TMFL and EMAT system that we discussed earlier. And in these pictures, you have the magnet bar with the north and south poles, like we talked about in the TMFL and EMAT. The magnetic flux enters the pipe wall through the weld and then back out the other side. And you can see in the picture, I'm pointing out the seam weld and the arrows to demonstrate that. Anomalies show the deviations from the signal, like the picture on the right. You can see the base material cracks and the small magenta lines pointing at them. And as well as the seam weld cracks where the black arrows pointing to the long seam weld and then small arrows as well pointing out the cracks along the seam weld. The goal is to achieve a small strip of data on or near the seam weld. You can go to the next slide, Daphne. Since the technology of the CMFL was developed, the technology has advanced, and these Hall effect sensors were used previously have gotten smaller. This really aided in slimming down the design and lowering the weight of the modules as well. So you can see the Hall effect sensors compared to a Canadian dime, which is about the size of an American dime, and against a ruler. The bigger one, the bigger black square, the Hall effect sensor, is the original size, and then the smaller one is now our current size. And this is also a mock-up of our first design of the Seam Weld Crack module. You can go to the next slide. So even with the sensor optimization, the robot is still a little heavy to maneuver. So we decided to move the center MFL that you can see in the first picture from the robot, and then just have two sensors. You can see how long the robot is with it having two sensors and removing the center MFL. We did a lot of analysis in terms of the tow force that the robot is capable of, as well as the distance between the centers matters, because as you saw, the communication between the leader and the follower is important to give it enough time to talk to each other before it moves into position. So these sensors would need to be displayed so far apart that they could still communicate. But then this robot at the bottom with the two drives is a lot longer than a normal size robot. And logistically, those upgrades would include a larger robot launcher, more software to control more drive modules, and therefore it just wasn't really feasible to change the robot that much to have two probes. So if you want to go to the next chart, Daphne. So I love this chart because it just shows how much work and effort goes into R&D and this design. We worked a lot on the robot configuration and the weights and the maneuverability, but ultimately it came down to one of these configurations. So for fun, in this presentation, there is an answer, but you know, for the final configuration, if you want to put your guesses in the chat or just keep it to yourself, but the different colors, I'll kind of go through them a little bit. They mean different things. So on the top left, you'll see a red box. That is the EMAT weld sensor. And there's a little blue box that jumps around, and that's our weld finder. And you can see how it's in between two drive modules. It moves to the nose. It comes back closer to, in concert with the weld sensor. And we've come up with many different designs. So if you want to go to the next slide. So here is the weld sensor that we chose. It's most optimal, as the Seam Weld sensor and weld finder are all in the yellow box in the center. One Seam Weld finder and probe in the center with 4 drive modules. Next slide. The capabilities of the Seam Weld sensor. This is the same R&D priority chart I showed in the beginning of the presentation. We met most of the priorities. It can detect actually oriented cracks at 1 inch in length or longer. It works on pipes with wall thickness of a 1/2 inch, and the robot is bidirectional. So it needs this, especially because the original, you know, the Explorer itself is bidirectional, but now that we are using one probe, we still want to get a full 100% data of the full length of the seam weld. So once the robot finds the girth weld, it will look for the seam weld, reverse slightly to the beginning of that seam weld to be able to collect 100% of a full scan of that seam weld from girth weld to girth weld. Next slide. So where are we today with this technology? Intero and Pipetel are working on commercializing this robot for 16-inch through 24-inch pipes. Summer last year, the 16-inch Seam Weld sensor completed a job with SoCalGas, and this concludes the NYSEARCH Seam Weld sensor program. Next slide. So we did get some questions before the webinar, which I think my presentation did answer some of them. And then there was one about the Explorer's range, which is the Explorer's range is about 1,600 feet on a single charge. But Pipetel has a tool called the inline charger, and it is able to charge the robot without being able to remove the robot from the pipe. And we also completed a project with Intero for an energy harvester, which is a module that can be installed on the robot to extend the range of the robot as well. And that does conclude my presentation. I don't know if there are any other questions.
Thank you, Suzy. Thank you, Daphne. I appreciate it. This is one of the true successes of our research program and funding and having this, as Travis said at the beginning, being able to utilize this technology and integrate it into our integrity management program is huge. We just keep trying to push that bar further ahead, which is great. So we have had a couple questions that have come in. Just looking to see real quick if there's any hands that are raised. It does not look like it at this time. So Gary Choquette, Gary, do you want to come off mute and ask, or should I just read your question? Okay, I'll go ahead and read Gary's question. What kind of distance can be covered based on battery life? Oh, Gary, is that? Did you get that, Suzy? They're asking battery life and distance.
Right, so about 1,600 feet on the single charge.
Okay.
Well, so distance depends on miters and other things in the line, as well as battery recharge, and energy harvesting, which is now completed, is designed to recharge the battery automatically. So Karen, I think we had notified you that Rod Lee and the Intero folks are also on the line. So I don't know if Rod Lee wants to chime in on that, but that's a big issue and it's a big question that we've been working on beyond this crack sensing program.
Rod, do you want to speak to that? Okay, we'll continue and carry on. Jim Wyman, you have your hand up. Would you like to come off mute and ask your question?
There we go.
Jim?
Yeah, I was going to say, well, let me come off mute. I apologize. So
Okay.
You said your sizes are 16 to 24 inch. Does that include dual diameter type lines, or is that just single diameter lines? Did you guys hear me okay?
I could hear you. Suzy, did you hear that?
Can you repeat the question? You're talking about dual diameter lines with one inspection. Can you repeat that?
Yes. Is it just a single diameter tool robot, or can you do, say, like an 1820, a 2022, 2026?
Right. So in one job, you have to have generally one size, although there's some variation in plus or minus 2 inches, because you have a module that might be 20 to 22 or 24 to 26. I think there's more experience by Pipetel and what they're doing in the field, but that's my understanding of we have different ranges, and then we have sub ranges within that you don't have to change the tool.
Okay, in your smaller diameter sizes, is there a time frame on development, say like of a 12 inch?
For the crack sensor?
Yes, ma'am.
So we did not fund that size range. I think that requires additional R&D, and when you go down in size, it's more redesign than when you go up in size. So there is not a time frame that I'm aware of for that size in 2023. I would defer to Intero and Pipetel on that too.
So Rod, I have unmuted you. I didn't realize I needed to unmute people. So if you want to add to that.
Hey, can you hear me? This is Rod here with Intero.
Yes.
Okay, perfect. Definitely, I think you did a great job answering that question on the multi-diameter questions. And I think there was a question prior to on the range of the robot. Again, I think Suzy, you did a great job. Yeah, on a single charge, Gary, your questions, the typical range is about 1/2 mile. But Suzy and Daphne alluded to there are technologies that we've been utilizing to expand that range.
Right, and we want to get to over 1 mile, and with certain flow rates and certain conditions, we've proven field testing that we can do that with energy harvesting. But in live jobs, I don't want to testify to where that has come, but it's going to continue to increase with the technologies that we're adding.
Great, thank you. Okay, so the next question is from Bill Amond, and he would like you to restate what the sensor technology is for the final seam sensor.
Right, so the final technology is the CMFL, which is the TMFL EMAT concept.
Okay, thank you. Okay, let me scroll through. So David Zhu, you put a question in the chat. Would you like to come off mute, or I will read your question? Let me unmute you. Hang on. I've made you able to go off mute if you want to ask your question specifically, Dave.
I always ask this question because email technology has a lot of progress in the recent years. Now, there's a module for small size pipe. I want to understand whether Pipetel has any plan to recheck the email. So the early time you said the email is kind of bulky, right, for small size pipe. But now there's a lot of progress in the email side. So will it be in the future any plan to reevaluate the feasibility of using email technology? Then you don't need to have the module just to locate the steam anymore, right? Just one tool.
Right, so we did look at the EMAT again for this project, but it was just too sensitive to debris.
Okay.
And always an issue. Okay, the next question is from Luli, and what is the resolution of your sensor?
In pixels, I don't know if we, I mean, it detects the cracks in seam welds down to, for certain weld thicknesses, right, Suzy? So I don't know if we have a quote on a resolution or we spec a resolution. And help me.
Yeah, I don't think we spec a resolution, but I know we can detect tight cracks, which is like 0.0002 inches or something along that line, opening of a crack. So yeah, I don't think I have a resolution number.
Yeah, Suzy, maybe I'll chime in here too. So you had a slide with the spec, right, with the specifications. The 25% depth of a crack. Again, this is not a full 360-degree full body sensor, right? So this sensor measures the seam weld and then plus minus 10 degrees either side of the long seam.
And there was a follow-on question where just wondering if they're needed to maybe be an additional sensor added, maybe for 3D imaging, or if there's any thoughts behind adding more?
I'll start with that. Maybe others can chime in. We focus today on crack sensing. The Explorer Robot has very high resolution visual sensors, ovality, mechanical damage sensors. I'm not an integrity expert like Travis, folks on the phone, but what I've seen graphically is quite impressive as far as resolution and imagery. I don't know if others want to weigh in on that one.
Okay, and Heather, I might need your help here. Oh wait, I found it. I lost my questions. Rod, I don't know if you want to chime in to add if there's like thoughts behind adding additional sensing capabilities, but as Daphne said, this is focusing on the crack sensor today.
So maybe I could also add, because we have this moment, other questions. We have worked on other sensors besides optical sensing for mechanical damage and ovality, crack sensing. The corrosion sensor was the first thing in 2010. We worked on a hardness tester, which is in essence sensing. So I don't know what other sensing folks have in mind, but I'm just trying to say that, in fact, the field of view on the visual sensors really gives you quite a bit of information.
Okay, thank you, Daphne. So is there a minimum length of crack to be detected?
1 inch, yes. And I think it is on one of my slides for you as well.
Okay, thank you. And I'm not sure that I understand this question, so I'm going to read it exactly. And maybe, considering that the system has evolved from a leader-follower configuration to a configuration where the seam locator and sensor are located in the same sensor head, does this slow down the pace of inspection?
So yes, it does.
Go ahead.
No, so it does slow down, but not by a lot. I do have, I think by seconds of how many, but I don't remember it off the top of my head. That was in part of our analysis when we were looking at that beautiful chart of 25 different robots, of how efficient and quickly this inspection could be done. So yes, it does slow down a little bit because the one probe needs to find the girth weld. Once it finds the girth weld, it needs to look for the seam weld and then reverse slightly to get a full 100 coverage of that seam weld. So it does slow it down a little.
Okay, thank you. Is there an actual pace? He's asking like feet per hour.
So the pace of the robot is 20 feet a minute. No, 20 feet an hour. No.
Yeah, it'd be going really fast.
Yeah, it's about 1,000 feet per hour, right? So
1,000 feet per hour. Yeah.
Perfect. Thank you. Okay, let's see.
I think we've talked so much about flow rate lately and stuff like that that we're
So there is I think it's sort of out of scope of this webinar, but there is a question that came in basically asking about the impact on using this robot and system with a hydrogen blend. And we'll just consider that as out of scope. And they were saying who in the world are working on that. And we know there's a lot of research that's underway and that still needs to be done.
I guess the point we were making in the one slide, Karen, I'll add, is that we may be repurposing the infrastructure that's already in place, and for proactively monitoring that infrastructure, it seems like that's something you can do with this technology.
Perfect, thank you. Okay, so that is the questions. Let me see if anyone else has raised their hand. Okay. Bill, I see that Bill Amond, we have two Bills that have hands raised. Bill Amond, you have a hand raised?
Yeah, I actually typed the question into the chat box, but my question is regarding the detection limits, roughly 1 inch by 25% of the wall thickness. But is that also true for all the different seam configurations there might be out there? Like you got flash weld seams that have a different shape than an ERW seam, and those have a different shape than single-sided subarc weld, which is a different shape than a double-sided subarc weld. Are those detection limits pretty much universally applicable?
Yes, they are. Yes.
Oh, perfect.
That's why we did the testing for like low, medium, high as sort of a characterization of all the different types of seam welds. But I know when they did testing in the lab, they did a bunch of different types of welds as well.
Hopefully that excites you, Bill.
Yep, that's yeah, I get excited about odd things, but that's one of them. Thank you.
Great, thank you, Bill. Bill Lighty, I'm sure I'm butchering your last name. Let me you can go off mute if you would like to ask your question.
Can you hear me?
Yes.
Great, thank you. This is Bill Leedy, the Leedy Foundation in Juneau, Alaska. There's a great deal of interest throughout the natural gas pipeline industry in whether we will be able to use the extant pipeline investment that we have for pipelining hydrogen, either as a blend or as high purity. And Chris Sanmarquis from Sandia National Lab in Livermore has said, to contemplate that seriously, you really must know the condition of the asset. And that means, are there hard spots in the welds? Are there flaws in or inclusions in the pipeline steel? Are there mechanical loads on the pipeline itself, perhaps ground movement? And thank you, Suzy, for sort of an update on the state of the art of smart pigs. What do we need from the NDE industry in order to determine the condition of the asset? What does that mean for considering whether and how we're going to be able to use this giant inventory of pipelines for hydrogen, either blended or high purity? Thank you.
So
I think, go ahead, Daphne.
I was just going to say, it's really an operations discussion for each gas operator. So Karen, were you going to?
I was going to say it's, I mean, knowing what we have in the ground and what our system is part of our integrity management program, whether or not we're introducing hydrogen, but I mean, that is definitely a challenge. I know we're addressing it. It's come up in various research forums, discussions across operators. And so how we approach it, what we do from a hydrogen blend perspective is, and there's a lot of ongoing questions that are being looked at, but we thank you for the question. But from what it sounds like, the hope is that a tool like this will be able to be adapted and continue to be used in a hydrogen blend environment, because it's definitely been beneficial to help answer some of those questions.
Yeah, Karen, if you can hear me, I might try to tackle that one just briefly.
Perfect. Thank you, Travis.
Okay, so I mean, it's a little off topic, but it's a little on topic too. I think you characterized it well. That's an integrity management question. Generally speaking, I don't think the approach changes. You're really fundamentally dealing with a crack management issue. And like all crack management issues, we need to understand the material response to the cracks. We need to be able to size those cracks, and then we need to be able to model their behavior. If we blend hydrogen, we can expect that the steel is going to become more embrittled, and then that's in turn going to lower or shrink the critical flaw size. And if we can survive that sort of initial transition to hydrogen, then we'll be facing a long-term fatigue crack management issue, potentially, along with any other issue that combines with cracks. So a tool like this, if we can harden it and make it friendly for a hydrogen environment, it would have its place within a blended environment, the same way it might have its place within a natural gas environment. It's just simply an adjustment to the critical flaw size we need to be looking for, and then an adjustment to the material's properties. So lots of questions to be answered in both of those columns, but the general approach doesn't change much. It just changes the particularities based on design requirements and based on operating conditions. So I see the place for all smart pigging and the place for this particular type of smart pig to be very similar to what we're experiencing today. Just looking for a different flaw size, really.
Thank you, Travis. So let me see if there's any other hands that have been raised. Doesn't look like it. Okay. So let me go ahead. It doesn't look like we've had any other questions get added as well. So let me see. Travis, is there anything else that you would like to add before we'll close out if nobody has other questions?
Nothing to add other than, for starters, I appreciate Rod Lee jumping on the call. You know, the same sort of incredible partnership that we've had with NYSEARCH is also reflected in consultants like Rod and his company. They're a critical partner in sort of the triangle of R&D that makes an endeavor like this successful. We've had nothing but great success and great support from Rod and his team. So again, I think it's an ideal partnership. It shows how R&D really can change the way we do work and the impact to safety for the customers and the employees that we serve and the employees that work at our companies. So nothing more to add. Just thank you for everyone's attention and attendance. Thank you to NYSEARCH, to Suzy, and to Daphne for walking us through it, to Rod for his support jumping in on some of the technical questions. And I hope that for the operators on the call who may have more questions, at SoCalGas, we've had the privilege of racking up a few miles with these tools under our belt. We'd be happy to help any of those who have questions on the practical end. There are a lot of practical considerations that you need to consider when using these types of technologies, and we're more than willing to share with the industry and to try to promote safety for everyone who's working on the safe and reliable delivery of natural gas. So just thank you to all, and thank you to the NYSEARCH team and to Rod and his team.
Thank you, Travis. So we do have a couple last minute questions, but so we'll have a couple comments coming in. See, you give them the last warning, and we have folks. Bill Amond, go ahead and come off mute.
Yeah, hi, thanks a lot. I just wanted to echo what Travis was saying in response to the question about what we need to do for hydrogen service. And coming at it from the standpoint of a service provider who's worked with a lot of different pipeline operators that all have similar questions about what their vulnerability to hydrogen service might be. I got to say, one of the considerations is that, you know, it's not a one-size-fits-all approach. A lot of different pipeline operators have a lot of different conditions and a lot of different knowledge base about their pipeline systems. So, you know, there's tens of thousands or more miles of pipeline that are out there, but no two pipeline systems are the same, and therefore the needs of those particular operators is also different. There's been huge strides that have been made in the last couple of years about how to learn more about a pipeline non-destructively and in situ in the ditch, about things like the mechanical properties. And I totally agree with what Travis was saying about the ability to learn more about what the flaws might be that are present. But the second part of that is knowing the mechanical properties of your piping. And the industry's making a lot of progress being able to do that, but it's definitely not a one size fits all, and some operators are better positioned to make a faster transition to hydrogen than others are. So that's it.
Great, thank you, Bill. Gary, will this just entertain one last question, and then we'll go ahead and wrap it up. Gary, did you put is that the question that's in the chat?
Yeah, that's correct. The ability for the tool to traverse that pipe we would call difficult to inspect. So through elbows, T's, risers, that type of stuff, is it able to navigate through complicated piping?
Yes, it is. Yeah. Sorry, were you going to say something, Daphne?
I didn't hear. I thought it was complicated. What was the piping you used? What was the word?
Yeah, complicated layout, difficult to inspect piping.
Absolutely, that's what it was designed for. Yeah, absolutely.
Thank you.
Perfect. So thank you all for attending. Great questions, great conversation, and thank you to Daphne and Suzy for coming on and sharing the technology. We will be following up, sending you just a link to a survey. So just kind of don't put it in your delete box. Maybe take a minute and let us know how we're doing, what you might like to hear in a future webinar, a topic, and then there are, as we mentioned, ways to reach out and contact us. In the GoToWebinar tools, you will see a little handout list. If you click the little arrow, make it go down, you can download the slides from today's presentation. And we thank you so much once again, and thank you, Daphne and Suzy. And
thank you, SoCal, for your leadership. Thank you so much.
Our pleasure. This is a good one. Yes. Hey, everyone, have a fabulous rest of your Thursday.